I'm going to talk in a little bit more detail about the order of operations, and when I'm done, Anne's going to talk about some calculator issues. Some of the examples that I'm going to do might seem like complicated enough examples that you want to pull out your calculator. I urge you not to do this though. I'd rather you wait until Anne tells you about some of the issues that come up with the order of operations in calculators, and then you can get some practice using your calculator with the order of operations. In specific, I'm going to talk about grouping symbols and the order of operations. And then I'm going to talk about how exponents come into play with the order of operations. And finally, I'm going to work on putting everything together so we can see how the order of operations works when we have all kinds of things going on in our problems. So let's start by looking at grouping symbols. Grouping symbols, such as parentheses, change the order of operations. Let's start by evaluating 6 minus the quantity 10 plus 2. Using the order of operations, this tells us that we need to work within the grouping symbols first. So the first thing I need to do is add 10 and 2. So then I have 6 minus 12. And 6 minus 12 is negative 6. Well, I want to look at this same problem, but in a little bit different way. So same problem again, 6 minus the quantity, 10 plus 2. But this time, I want to use the distributive property. To use the distributive property, first I'm going to rewrite this as an addition instead of a subtraction. So I'm going to write this as 6 plus negative 1 times the quantity, 10 plus 2. And then I'm going to distribute the negative 1 through the parentheses. So I would have 6 plus negative 1 times 10 plus negative 1 times 2. And if you want, you can do that multiplication in your head. I just want to make sure we see that we're distributing here. So negative 1 times 10 and negative 1 times 2 have to be done before the additions. The order of operations tells me I need to multiply before I add. So I would have 6 plus negative 10, the product of negative 1 and 10, plus negative 2, the product of negative 1 and 2. And I can rewrite this without the addition symbols as 6 minus 10 minus 2. Now it looks like I've gone through a lot more steps already here, and I still have a couple more steps to complete the problem. What I want to point out right now, though, is that when we work with a distributive property that has subtraction, to move that subtraction or move the negative sign through the parentheses and remove the parentheses, we just need to change the sign of the numbers in the parentheses. So if we look at the original problem, we had 10 plus 2 in parentheses. If we look at the step we are on right now, we have minus 10 minus 2. We've essentially changed the signs. And it's going to get to a point where you can skip all of these steps in between and go right from the original problem to 6 minus 10 minus 2. Let's go ahead and finish this and make sure we get the same result as we did when we used the order of operations. So working left to right, 6 minus 10 is negative 4, and I still have to subtract 2. Negative 4 minus 2 is negative 6. When we worked this problem using the order of operations, we also got negative 6. Looking at the example worked in two different ways, obviously this took a lot longer than using the order of operations. Again, all that I wanted to point out here is when we distribute a negative through parentheses, essentially it changes the signs of the numbers in parentheses. I wouldn't expect you to ever go through all of these steps to solve a problem like this. Let's do one more problem using the distributive property. This time I have 6 minus the quantity negative 2 plus 5. Rewriting this as an addition problem, I would have 6 plus negative 1 times the quantity negative 2 plus 5. So I need to distribute the negative 1 through the parentheses. That is, I need to multiply negative 1 by negative 2, and I need to multiply negative 1 by 5. In the order of operations, we multiply before adding, so I'm going to do these two multiplications. So I have 6 plus 2, the product of -1 and -2, plus -5, the product of -1 and 5. And rewriting this just a little, 6 plus 2 minus 5, this shows us that when we distributed the negative through the parentheses, once again what we did was changed the signs of the two numbers in parentheses. I started out with -2 plus 5 in the parentheses. At this point, I now have plus 2 minus 5. I changed the signs. So let's go ahead and finish this. 6 plus 2 is 8, and I still have to subtract 5. 8 minus 5 is 3. Now let's evaluate the opposite of -10 plus 13. And I want to rewrite this just a little bit. Same thing I did with the last two examples with the distributive property. The opposite of -10 I can also think of as -1 times -10 plus 13. The reason I rewrote this is to make it apparent that we have a multiplication going on here and addition. And the order of operations says multiplication comes before addition. So the first thing I would do is -1 times -10, which is positive 10, plus 13. And 10 plus 13, of course, is 23. So when we come across a problem that involves something like this one, which had the opposite of -10, if we kind of think of that in our minds as multiplication, it will remind us that when we run across an opposite symbol, we find the opposite of the number before we add, in this case, or subtract if there were a subtraction in the problem. Now let's evaluate another problem using the order of operations. This time I have 4 times 3 minus 10 plus 6 divided by 2. The order of operations tells me multiplication and division come before addition and subtraction. So I have one multiplication I want to do here and one division I want to do here before I can do the subtraction and the addition. 4 times 3 minus 10, I can't do the subtraction yet. I do need to do this division though. 6 divided by 2 is 3. And I'm adding the 3. So I have 12 minus 10 plus 3. Subtraction and addition have the same priority in the order of operations, so I just work from left to right now. 12 minus 10 is 2, and I'm still adding 3. 2 plus 3 is 5. Now I want to look at a very similar problem to the one we just did. If we look at the problem that we just worked through and compare this to what I'm going to evaluate now, all that I've done is put parentheses around the 10 plus 6. So this time I'm evaluating 4 times 3 minus the quantity 10 plus 6 divided by 2. Grouping symbols change the order of operations. Now we need to start by simplifying what's in the grouping symbols. That means I need to add the 10 and 6 as my first step. So I have 4 times 3 minus 10 plus 6 is 16 divided by 2. Now I have a multiplication, a subtraction, and a division. Multiplication and division come before subtraction in the order of operations. So let's find 4 times 3 is 12. 16 divided by 2 is 8. And I'm subtracting these numbers. 12 minus 8 is 4. Notice we did get different results when we put the parentheses in. Our first example, we got 5. This example, we got 4. Grouping symbols change the order of operations. Now let's evaluate 10 minus 5 times the quantity 4 plus 6. The reason I want to look at this problem is because it's real tempting to do the first operation that you see. When I look at this, my eyes are drawn to that 10 minus 5, and it would be really easy to subtract 5 from 10. However, the order of operations tells me I need to add the 4 and 6 in the grouping symbols first. So I have 10 minus 5 times 4 plus 6 is 10. Now I have a subtraction and a multiplication. Multiplication comes before subtraction in the order of operations, so I'm going to multiply that 5 and 10. leaving me with 10 minus 50. And 10 minus 50 is negative 40. When evaluating expressions with nested grouping symbols, work from the inside out. You might ask, what do I mean by nested grouping symbols? Well, if I had something like square brackets 5 minus 3 times the quantity 2 plus 7, we call these nested grouping symbols. I have the parentheses inside the square brackets. The parentheses are nested within the square brackets. I could also write this with all parentheses. And sometimes you'll see things written that way, but you might agree that the way I wrote it first with the square brackets and the parentheses is a little bit easier to read because it's a little bit easier to tell where the parentheses begin and end. Here you have to pay attention to what's your innermost set of parentheses. With the square brackets and the parentheses, it's a little bit easier to tell. Another type of grouping symbols that often show up with these nested grouping symbols are the curvy brackets. Well, let's evaluate a problem using these nested grouping symbols. This time I have 5 minus the quantity 2 minus 6 divided by 3 plus 10. Since I have nested grouping symbols, I need to work from the inside out. I need to start by subtracting 6 from 2. So I have inside the square brackets 5 minus 2 minus 6 is negative 4. And the rest of my problem divided by 3 plus 10. I still have grouping symbols, so I still need to work the grouping symbols before anything else in this problem. I have 5 minus negative 4. This is the same as 5 plus the opposite of 4, or just 5 plus 4. That's 9, divided by 3 plus 10. Division comes before addition in the order of operations, so I'll divide 9 by 3. That leaves 3, and I still have to add 10. So I get 13 for the final answer. Here's another problem with nested grouping symbols. Here we have the quantity 40 minus 5 divided by the quantity negative 13 plus 20, all within square brackets. And then I'm multiplying by the quantity 1 minus 10 divided by the quantity 8 minus 5. That division's also within those square brackets. So I need to start with my innermost grouping symbols. I need to do my subtractions and additions within those parentheses first. 40 minus 5 is 35. So I have 35 divided by negative 13 plus 20 is 7. This was inside those square brackets. And then I'm multiplying by, in my square brackets over here, I'm going to work within the parentheses first. 1 minus 10 is negative 9, divided by 8 minus 5 is 3. So I need to still deal with the grouping symbols before I can multiply. So I'm going to do both of the divisions within the grouping symbols. 35 divided by 7 is 5, times negative 9 divided by 3 is negative 3. And 5 times negative 3 is negative 15. Now you might agree that the expression that we just evaluated was kind of ugly. There's actually another way to write this, and I'm just going to focus on the first set of square brackets here. So the expression 40 minus 5 divided by negative 13 plus 20, which is the expression that was in the square brackets in the last problem, can be rewritten with a fraction bar as 40 minus 5 in the numerator over negative 13 plus 20 in the denominator. A lot less symbols to write. In algebra, we often use fraction bars as opposed to the division symbol. In fact, very soon you're going to stop seeing the division symbol and start working with the fraction bar and seeing the fraction bar a lot more often. When we see the fraction bar, we need to treat it as a grouping symbol. We're going to simplify what's in the numerator and the denominator separately before we divide, just like we did with the grouping symbols. 40 minus 5 is 35, negative 13 plus 20 is 7, and 35 divided by 7 is 5. Now a fraction bar, also called a vinculum, is another grouping symbol. When we're working with fraction bars, we need to remember to evaluate the expression in the numerator and the expression in the denominator following the order of operations. Once we've done that, then we can divide the results. As an example with this fraction bar, let's evaluate 3 times the quantity 4 plus 3 times the quantity 10 minus 8. And all of this is over 18 divided by the quantity 4 minus 7. So we want to work with the numerator and denominator separately using the order of operations. In the numerator I have nested grouping symbols, so I need to start with those parentheses, and I'm going to subtract 8 from 10. So I have 3 times the quantity 4 plus 3 times 2, which is 10 minus 8. And I just have one set of grouping symbols that I need to start with in the denominator. So I have 18 divided by 4 minus 7 is negative 3. Now in the numerator I still have grouping symbols, and within those grouping symbols I have an addition and a multiplication. Multiplication comes before addition in the order of operations. So I'm going to multiply that 3 times 2. And 3 times 2 is 6. So in the numerator I have 3 times the quantity 4 plus 6. In the denominator all I have left is a division. 18 divided by negative 3 is negative 6. Finally, I need to add the 4 and 6 in the grouping symbols in the numerator. 4 plus 6 is 10. So my numerator simplifies to 3 times 10. My denominator is still negative 6. Now I can multiply in the numerator. 3 times 10 is 30. I'm dividing 30 by negative 6, which gives me negative 5. Now let's evaluate the square root of 9 plus 16. If I add 9 and 16, I get 25. So I'm finding the square root of 25. What I need to look for here is what positive number squared gives me 25. That number is 5. A radical symbol, which could be a square root like we just looked at, a cubed root, or any other root for that matter, is another grouping symbol. So let's compare the square root of 9 plus 16 that we just looked at. That again was the square root of 25, which was 5. Let's compare that to the square root of 9 plus the square root of 16. These two expressions look kind of similar. They both have square root symbols, they both have addition. What makes it different is the length of the square root symbol. In the first problem, square root of the quantity 9 plus 16, our radical symbol is a lot longer. It encompasses the 9, the 16, and the addition. The problem I'm going to work now, the radical, in fact there are two separate radicals. One radical is just over the 9, one radical is over the 16. The addition is outside. So this time I find the square root of 9, which is 3, plus the square root of 16, which is 4, and I get 7, a very different result. The radical symbol again works as a grouping symbol. You want to pay attention to the length of the radical so you know what to do first. Now let's talk about exponents. In an exponential expression like 3 squared, the 3 is called the base, and the 2 is called the exponent. When we look at 3 squared, we can think of this as repeated multiplication. 3 squared means we take our base 3 and we multiply it by itself 2 times in this case because our exponent is 2. So we could write 3 squared as 3 times 3. Here's another exponential expression, 2 to the 4th. If I want to write this in expanded form, I'm going to think of this again as repeated multiplication. 2 is being multiplied by itself 4 times. So this is 2 times 2 times 2 times 2. What I have written above, 2 to the 4th equals 2 times 2 times 2 times 2, is equivalent to saying 16 equals 16. 2 to the 4th is 16, and 2 times 2 times 2 times 2 is 16. If I take an equation like 16 equals 16, and I multiply both sides by 3, I still have an equation that is true. 3 times 16 is 48. 3 times 16 is 48. So the equal sign still makes sense here. What I want to do is take my equation that I wrote above, 2 to the 4th equals 2 times 2 times 2 times 2, and multiply both sides of that equation by 3. Again, I won't be changing anything because I'm still going to have 3 times 16 on both sides of my equal sign. Now the reason I wanted to do this is to point out that when we're exponentiating, when we have a power, we need to take our powers before we multiply. And it's a little bit easier to see when we have it written out this way. If we have 3 times 2 to the 4th, we can also write this as 3 times 2 times 2 times 2 times 2. So we're multiplying our 2's together first. That's our exponentiating, or our raising to the 4th power, and then we're multiplying by 3. If we had tried to multiply first, 3 times 2 to the 4th, and we thought, okay, 3 times 2 is 6, but I still have that exponent of 4, then I have 6 to the 4th, and 6 to the 4th is a lot larger than 3 times 2 to the 4th. So these are not equal to one another. This leads us to one of our properties in our order of operations. In the order of operations, we exponentiate before we multiply or divide, but after dealing with grouping symbols. Well, I want to recall that when we multiply something like 25 in this case by -1, all that it does is change the sign of our number. -1 times 25 equals -25. Now I want to take those 25s and I want to replace those with 5 squared, because 5 squared is 25. Well, this now says that -1 times 5 squared is equal to the opposite of 5 squared. This is actually going to be helpful for us to remember when we encounter something like the opposite of 5 squared. If we can remember that that's the same as -1 times 5 squared, and we remember our order of operations, then we'll remember to exponentiate, or raise 5 to the 2nd power first before multiplying by -1. Let's look at some examples of that. Let's compare the opposite of 5 squared and -5 squared, or -5 in parentheses squared. So we just said that the opposite of 5 squared is the same thing as -1 multiplied by 5 squared. We exponentiate before we multiply in the order of operations, so we take our 5 squared first, which is 25, and multiply that by -1. And we get -25. However, if the -5 were in parentheses and the power were on the outside, this is now telling me my base is -5. So I need to take -5 and multiply it by itself 2 times. -5 times -5 is +25. So the important thing to notice here is that these parentheses make a difference. We're getting 2 different answers. -25 for the first example, the opposite of 5 squared, and +25 when we square -5. Let's look at another example. What if I have -3 raised to the 4th power, where the -3 is in parentheses and the 4th power is on the outside? Now this means take my base, which is -3, and multiply it by itself 4 times. So this is -3 times -3 times -3 times -3. Now I have an even number of negative factors, so my result should be positive. And if I just multiply the 3's together, 3 times 3 is 9, times 3 is 27, times 3 is 81. So I have a positive result, and that is 81. Whereas if I had the opposite of 3 to the 4th, remember we can think of this as -1 times 3 to the 4th. We exponentiate before we multiply. 3 to the 4th, well, I just figured that. That was 81. And I need to multiply that by -1. So I get the opposite of 81, or -81. Again, the parentheses made a difference. Another way that you might be able to remember the difference between these two problems is with the parentheses, our base was -3. The exponent applied to the 3 and the negative symbol as well. When we have the opposite of 3 to the 4th, the exponent only applies to the 3, not the negative or the opposite symbol. So we exponentiate first, we find our 3 to the 4th first, and then we take the opposite of that. Now let's compare -2 raised to the 3rd power, where -2 is in parentheses and the 3rd power is on the outside. So our base is -2. We need to multiply -2 by itself 3 times. -2 times -2 times -2. I have 3 negative factors, an odd number of negative factors. My result should be negative. 2 times 2 times 2 is 8. So I get -8. Now let's look at the opposite of 2 cubed. When I have the opposite of 2 cubed, again, I can think of that as -1 times 2 cubed. So I find 2 cubed first, which is 8, and multiply that by -1. And I get -8. Notice this time I got the same answer for both of these expressions. -2 cubed is -8, and the opposite of 2 cubed is -8. Even though our operations were different, the reason I got a negative in the first example is because I had an odd number of negative factors. I was multiplying -2 by itself 3 times. When we multiply an odd number of negative factors together, we get a negative result. Whereas in the example, the opposite of 2 cubed, this is like multiplying -1 times 2 cubed. There's still an odd number of negative factors, but this time it's just the -1. So when our exponent is odd, we're going to come out with the same result whether we have our number -2 in parentheses or outside of parentheses. Now let's compare 3 times 4, that whole product raised to the 2nd power, and 3 times 4 squared. So the 3 times 4 in parentheses tells me I need to deal with grouping symbols first. I need to multiply before I exponentiate. So I need to multiply 3 and 4. That gives me 12. And I'm squaring 12. 12 squared is 144. Now let's look at 3 times 4 squared. 3 times 4 squared. Now I have a multiplication and a power. Powers come before multiplication in the order of operations. So this time I need to square the 4 first and then multiply that result by 3. So I have 3 times 4 squared is 16. And 3 times 16 is 48. I get 2 different results. 144 is definitely not equal to 48. Parentheses change the order of operations. We exponentiate before we multiply, but we always start with our grouping symbols or our parentheses. So let's put all of this together. Let's see how the order of operations works when we put everything together. First, we perform all arithmetic that occurs inside grouping symbols, such as parentheses. We also talked about radical symbols being grouping symbols, fraction bars being grouping symbols. All of the grouping symbols come first. Then we evaluate all powers, that is, exponential terms or factors. Next, we perform all multiplication and/or division left to right. And finally, perform all addition and/or subtraction left to right. Now, if we look at all of these rules, this looks like a lot to remember. What some people like to do is use this little mnemonic device. Please excuse my dear Aunt Sally, to help them recall the order of operations. Well, let's look at how this mnemonic device can work for us. So we start with the phrase, please excuse my dear Aunt Sally. We start with the word please. The P in the word please is to remind us we start with parentheses. Parentheses and all other grouping symbols have first priority in the order of operations. Then we move on to excuse. The E in excuse is to remind us about exponential factors, or terms, that is powers, which are evaluated next in the order of operations. The next words come in pairs. My dear come together because multiplication and division have the same priority in the order of operations. The M in my for multiplication and the D in dear for division. And then our last pair, Aunt Sally. The A in Aunt is to remind us about addition, and the S in Sally is to remind us about subtraction. Addition and subtraction have the same priority in the order of operations, and they come last. Now I want to turn over to Anne, who's going to talk about some of the calculator issues with the order of operations.
In this part of the lesson, we're going to talk about some issues that come up when we try to use our calculator to perform arithmetic. Now, we've spent a lot of time talking about the order of operations, and you might think, hey, I'm going to pull out my calculator and do all my arithmetic on the calculator, and then I don't have to think about any of these issues of the order of operations. But it turns out we really need to know the order of operations to use our calculator well. So the things we're going to talk about in this part of the lesson, first we're going to start by just looking at order of operations on the calculator. We're going to spend a little bit of time looking at just grouping symbols and how they work. And finally, we're going to work with some fractions on the calculator. So let's start with the order of operations. Now, the first thing we're going to see is that not all calculators know the order of operations. So for us, it's important to know both the order of operations and how our calculators operate in order to use the calculator intelligently. So we're going to start with a simple example. In fact, all the examples we're going to do today, the arithmetic is going to be real easy, and we're doing this so that we can compare the results we get when we do the arithmetic with pencil and paper to what we're going to get on the calculator. So let's start with 100 minus 20 times 5. We know to perform the multiplication before the subtraction. So when I multiply 20 times 5, I get 100, and I know the result is 0. So let me pull out a scientific calculator and do this problem. So I'm going to enter the problem just like it's written on the page. 100 minus 20 times 5. Oops, 400. I had gotten 0 when I had done this by hand. So what happened? Let's do this quickly again. 100 minus 20, and when I hit the multiplication, notice what the calculator did. It performed 100 minus 20, and then multiplying 80 by 5, that's where the 400 came from. So the calculator calculated 100 minus 20 times 5 to get 400, which is not what we wanted to do. The calculator performed the first operation it saw. Well, if your calculator operates like this, you might ask, well, how can I get the right answer out of my calculator? And what you can do is enter grouping symbols to tell the calculator what the order of operations is. So what we really want to do is do 100 minus, and then I'm going to use the parenthesis keys that are here on my calculator and put the 20 times 5 in parentheses, and now I'll get 0. So in my calculator, what I entered was 100 minus parentheses around the multiplication. Now the calculator knows to do multiplication before subtraction. Now on this scientific calculator, I can actually tell it to use the order of operations. And if you have a calculator like the one I just showed you, this is probably not possible. But this is a fancy computer calculator, and I'm going to change the logic from performing the operation as entered, so it did the operations from left to right regardless of the order of operations, to algebraic. And this is telling the calculator, use the order of operations. So when I do the same simple example that we've been working with, 100 minus 20 times 5, it gives me the correct result. So some scientific calculators know and use the order of operations the same way we do. other scientific calculators do not. It's important for you to figure out how your own calculator works. Now let's talk about grouping symbols. I'm going to start with a problem that uses nested grouping symbols. And the first thing I'm going to do is do this by hand. So I have 3 times the quantity, 6 minus 10 divided by 2. So I'm going to first perform the operation inside the innermost parentheses. 6 minus 10 is negative 4, which I'm going to divide by 2. Now I'll perform the operation inside the square brackets. Negative 4 divided by 2 is negative 2. And when I perform the multiplication, I end up with negative 6. So I know what the result needs to be. Now I'm going to pull up my scientific calculator just for a moment and point out that on the scientific calculator, I just have parentheses. I don't have anything like a square bracket. So when I do this calculation on the calculator, I only can use parentheses. I'm going to close my calculator for a moment, and I want to show you how I'm going to enter this on the scientific calculator. I'm going to do 3 times, and I can just use parentheses. So I'm going to need 2 sets of parentheses. 6 minus 10 divided by 2, close parentheses. This is what I will enter in my calculator. Also notice that I was explicit about multiplication. When we see something like this, 3 next to a grouping symbol, we know to perform multiplication. But our calculators aren't that smart. If we want the calculator to perform multiplication, we need to tell the calculator to perform multiplication. So let me perform this operation as I wrote it on the page there. 3 times, open parenthesis, 6 minus 10, close parentheses, divided by 2, close parentheses, equals negative 6. Now I want to pull up a graphing calculator. This is a TI-89, and just quickly show you that the TI-89 also has parenthesis keys. Now, right above the parenthesis keys are braces or curly brackets, and next door are square brackets. But these orange symbols here on my calculator do not function as grouping symbols. They have other functions on this calculator. So on this graphing calculator, just like on my scientific calculator, the only type of grouping symbol I'm going to use is a parenthesis. So some calculators, such as the TI-89, have square brackets and curly brackets in addition to parentheses. The square brackets and curly brackets have different functions on these calculators. These brackets are not used as grouping symbols. So now let's look at another example where grouping symbols matter. We're going to compare the opposite of 5 squared with the quantity negative 5 squared. And as you know, the opposite of 5 squared is negative 25. But negative 5 itself raised to the second power is positive 25. So I want to show you how to enter negative numbers on your calculator and how to raise something to the second power. So going to the scientific calculator, I have a key here that says plus or minus, and this changes the sign of a number. Now, if I want to enter negative 5, it seems like I would enter it just the way I said it, negative 5. But that didn't do anything. I got positive 5. So you'll notice that on many scientific calculators, you'll need to enter the number first and then change the sign. So I just entered negative 5 into the calculator. So when I want to calculate the opposite of 5 squared, I want to square 5 first and then take the opposite. So I'm going to take 5 and square it and then take the opposite. So one of the things that's actually nice about this funny way of entering negative numbers in the calculator is it reminds us that we need to square 5 first before taking the opposite. Now to do the other problem, I'm going to use parentheses. And I'm going to put the negative 5 in parentheses. So I'm going to open parentheses, type in negative 5, close parentheses, and then square it, and I get the correct result. Let me just quickly show you on a graphing calculator how the negative works. Here I have my negative key down here by the enter, and this is fairly common on a lot of the graphing calculators. This key is different than the subtraction key. And if I want to enter negative 5 on this calculator, I simply just enter negative 5. Now if I want to square negative 5, I use this key here to raise something to a power. This is called a caret key. I'm going to raise negative 5 to the second power. Well, why didn't it give me positive 25? Well, again, this calculator is being literal. It actually calculated the opposite of 5 squared. If I want to do this calculation here, I need to use parentheses. Put negative 5 in parentheses and then square it to get the positive 25. Now let's look at an example using a radical. We know that the square root of 9 plus 16 is the square root of 25, which equals 5. This is the number we should get out of our calculator. We have a square root key. And the square root key on this calculator functions the same way as the negative does. If I take 9, then I hit the square root, the calculator gives me the square root of 9. Now the machine is very literal. If I type in 9 plus 16 and then take the square root, what the calculator did in that situation is it only took the square root of 16. And it said that 9 plus the square root of 16 is 9 plus 4, which is 13. So what I'm going to do to get the right number out of my calculator is I'm going to put the 9 plus 16 in parentheses and then take the square root. So when I entered this into my calculator, I put the expression under the radical in parentheses. On my graphing calculator, when I hit my square root key, it reminds me that I need parentheses around the expression under the radical. I just need to remember to close the parentheses when I'm done. Finally, let's look at fractions on the calculator. Now the fractions we're going to be looking at are not things like adding 1/2 plus 1/3, but we're going to look at the fractions where the fraction bar is used as a grouping symbol. So the examples we're looking at again are really easy. We know from the order of operations to treat the fraction bar as a grouping symbol and to multiply 7 times 5 first before dividing. So when we plug this number into the machine, we should get 1. So I'm just going to work these examples on the scientific calculator, and I'm going to enter 35 divided by 7 times 5. Oops, I didn't get 1. So what happened here? Well, I entered 35 divided by 7 times 5. I hope you can see what happened. Calculator's literal. It knows the order of operations. It knows that division and multiplication have the same priority, and the operations were performed from left to right. So the calculator did 35 divided by 7 and multiplied it by 5 to get 25. So we used a division symbol to indicate the fraction bar. But this division symbol to the calculator just means division. It doesn't understand it as a grouping symbol. So what I would need to enter here is 35 divided by 7 times 5 grouped using parentheses. Now I'm telling the calculator to understand the division as a fraction bar and as a grouping symbol. So let me try this again. 35 divided by 7 times 5 in parentheses, I get the correct answer, 1. A slightly different problem. Again, we know what we should get. This is going to be 35 divided by 35, which is just 1. So now I'm going to think ahead. I'm going to put in my parentheses to tell the calculator to group the expression, do the operation in the numerator first. So parentheses, 7 times 5, close parentheses, divided by 35 equals 1. Everything is right in the world. My calculator is giving me the answer I expected. Now suppose I wasn't paying attention a couple of minutes ago and I just entered this problem the way it was written. 7 times 5 divided by 35. I got the right answer. So even if I wasn't paying attention to myself just a moment ago, if I left the parentheses out, I got the correct answer. And the reason why is, think about the order of operations. This multiplication is performed before this division. So these parentheses are really redundant. We don't need them. By the order of operations, this multiplication is performed first. So these parentheses are for emphasis. In the last example, these parentheses are essential. Now, I put these parentheses in because it's a habit I'm in, and the reason why I'm in this particular habit is for when I see a problem like this. I'm going to quickly do the arithmetic here without a calculator. 12 divided by 6 is 2. Now when I pull out my calculator, I'm going to tell the calculator to perform the operation in the numerator first and then divide by the denominator. In this situation, we have addition and division. Without these grouping symbols, the division would be done before the addition, which is not what we intended. So in this situation, the parentheses are essential. So I often use, in problems with fraction bars, parentheses, whether or not they're essential. That way I know I'm always using them when I need to be using them. So let me quickly just do this on the calculator, make sure it works. Open parentheses, 7 plus 5, close parentheses, divided by 6 equals 2, which is exactly what we'd expect. So I just want to finish off by giving you some advice. You should practice some simple calculations on your calculator until you feel comfortable using the calculator as a tool. As we did in this part of the lesson, choose problems for which you know the result without using the calculator, and then you can check to see if your calculator is giving you the results you expect. With that, we'll end this part of the lesson.